Have you ever wondered how large language models like ChatGPT manage to generate such coherent and contextually relevant text? It's not magic, it's a revolutionary mechanism called attention. Welcome to How Transformers Think, a plain English walkthrough of attention. Today, we're going to demystify the heart of modern AI. We'll start by understanding what attention is and why it's so crucial for transformers. Then we'll dive deep into its architecture, explore a real-world application like machine translation, and finally look at the exciting future of this incredible technology. By the end of this session, you'll have a clear grasp of how attention allows AI to think and understand relationships within data. At its core, the attention mechanism is about allowing a neural network to focus on specific, relevant parts of its input when processing information. Think of it like this. When you read a complex sentence, you don't give equal weight to every single word. You subconsciously highlight the most important words and phrases that give the sentence its meaning. Attention does something similar for AI models. It helps them decide which parts of the input sequence are most relevant for generating the next output. To achieve this, attention uses three fundamental components, often represented as vectors: the query, the key, and the value. The query is like asking a question. The keys are like labels or indices for information, and the values are the actual pieces of information. The model compares the query to all keys to determine how much attention to pay to each value. Now let's zoom in on self-attention, which is the cornerstone of the transformer architecture. In self-attention, the query, key, and value vectors are all derived from the same input sequence. Imagine a sentence: the animal didn't cross the street because it was too tired. When the model processes it, self-attention helps it determine whether it refers to the animal or the street. The process works like this. Each word's embedding is transformed into its own query, key, and value vectors. The query of a word is then compared against all other keys in the sequence using a dot product. This dot product result is scaled down and then passed through a softmax function to get attention weights. These weights determine how much each value contributes to the output for the current word. To capture different aspects of relationships, transformers employ multi-head attention. This means instead of one set of Q, K, V transformations, there are multiple parallel sets, each learning to focus on different types of relationships. The outputs from these heads are then concatenated and linearly transformed, providing a richer, more comprehensive understanding of the input. Let's see attention in a practical scenario: machine translation. Before transformers, translating long sentences was challenging because models struggled to remember the beginning of a sentence by the time they reached the end. The transformers encoder-decoder architecture, powered by attention, revolutionized this. The encoder processes the input sentence, say in English, using self-attention to build a rich, contextual representation of each word. The decoder then generates the output sentence, say in French, word by word. Crucially, at each step of generating a French word, the decoder uses an attention mechanism to look back at the entire encoded English sentence. It decides which English words are most relevant to generating the current French word. This allows for precise alignment, even if the grammatical structures or word order differ significantly between languages. For instance, when translating "the cat sat on the mat," the decoder can focus on cat when generating shot and mat when generating tapis, ensuring accurate and contextually appropriate translation. Attention is undeniably a fundamental breakthrough, driving the incredible progress we've seen in AI, from natural language processing to computer vision. It's the engine that allows these models to process vast amounts of information with unparalleled contextual understanding. Looking ahead, the field is rapidly evolving. Researchers are constantly developing more efficient attention mechanisms to tackle the high computational cost, especially with ever-growing input sequences. We're seeing innovations like linear attention, sparse attention, and various approximations that aim to extend context windows without prohibitive resource demands. However, challenges remain. The computational complexity is significant, and while attention helps us understand what the model is focusing on, fully interpreting why it makes certain decisions is still an active area of research. To truly master this space, I encourage you to delve deeper into papers on attention variants and explore how they're being applied in different domains. The journey into how AI thinks has just begun.